Good morning, Internet. I am Matt Buyak, and in this video, we're going to take another look at the 29th problem from the Project Euler Problem Archive. Now, in the last video, we solved this problem using C++ and our big integer class. In this video, we'll solve it using analysis alone. Now, just to refresh your memory, this problem asks us to find integers of the form a to the b, where a and b are on the range 2 to 100 inclusive. Specifically, it asks us to count the number of distinct integers of this form. So let's get into it. As usual, we'll open up our problem directory and analysis file. And the first thing that I would note about this problem is that our search space is going to be of size 99 squared. And that just comes from the fact that A has 99 possible values, B has 99 possible values, and so our search space is going to be 99 squared. And if each integer of this form had only one possible representation, then this would be our answer. We would be done. Of course, that wouldn't be a very interesting problem, and so we'll note that as an example of a duplicate representation, we have 2 to the 60th is equal to 4 to the 30th. So this might suggest a strategy of finding duplicates and subtracting the number of duplicates from 99 squared. And that is, in fact, the strategy that we're going to take. However, it's a little bit more complicated than it may seem at first. If each integer had exactly 2 possible representations, we would just count the number of representations which have duplicates, divide that number by 2, and subtract that from 99 squared to get our answer. However, we'll note that going back to 2 to the 60th, that this is also equal to 8 to the 20th, or 16 to the 15th, or 32 to the 12th, or 64 to the 10th. And so there are cases such as this where we have more than 2 possible representations, and it's pretty easy to see that the number of representations for a given integer can vary quite widely. Okay, so in attempting to count our duplicates, perhaps consider again our example here, and we'll note that 5 of these are going to be counted as duplicates, and 1 is going to be counted as canonical. That is, when we're subtracting our number of duplicates from our search space size, we only want to consider 5 of the 6 representations as duplicates. And so we will need to decide on a convention for determining our canonical representation. And so we'll say definition. The representation of a given integer with the largest base will be considered the canonical representation. And so then this allows us to define what a duplicate is. We'll say an ordered pair A comma B is considered a duplicate if there exists x comma y such that a to the b equals x to the y, and a is less than x. Okay, so now we just need to find, for given values of a and b, what are the conditions under which x and y exist. And that will bring us to the second part of our video, our analysis. Okay, so let's start by saying let n be the greatest common divisor of b and y. And we'll also say let d be b divided by n, and let c be equal to y divided by n. That is, we're just factoring out the greatest common divisor of our exponents. And so that's going to give us something like a to the dn is going to be equal to x to the cn. And we'll just note, because we know a is less than x, it must be the case that c is less than d. Okay, we'll also note that x is going to be equal to, actually before we do that, let me just say that the advantage of this approach here is that it lets us take both sides of our equation to the 1 over nth power. That is, taking the nth root of both sides of our equation. And so that's going to give us a to the d is equal to x to the c. We'll also note that c and d are relatively prime. So this is because we factored out the greatest common divisor, and so now we have a situation where our exponents are relatively prime. And that's going to have certain advantages. Okay, so now we can take our equation, take both sides, or take the c root of both sides, and that's going to give us that x is equal to a to the d over c. And so we can look at the conditions under which this will cause x to be an integer. We know that x is an integer, and so let's say let g be the greatest common divisor of the exponents of the prime factorization of a. And we'll note that a to the 1 over g is an integer. And that's because of how we've defined this value g, because it divides all of the exponents in the prime factorization of a to the 1 over g must be an integer. We'll also say let a be equal to, that is capital A, be equal to a to the 1 over g. And note that means that a is equal to capital A to the g. And this lets us write our equation as x equal to capital A to the g to the d over c. Okay, so now let's suppose that P is some prime which divides C. Note that either P divides D, P divides G, or A to the 1 over P is an integer. But we'll note that because we factored out the greatest common divisor from the prime factorization of lowercase a, that means that capital A is not a power. And so that means that a to the 1 over p cannot be an integer. We've already noted C and D are relatively prime. Therefore, P divides G. And because this is true for all primes P which divide C, also, therefore, C divides G. Okay, and so let's just give that a name. We'll say let M be equal to G divided by C. And we'll note that, therefore, G is equal to MC. Okay, so substituting this back into our equation, we can come up with values for A, B, X, and Y in terms of M, C, N, and D. And so in particular, we'll have that lowercase a is going to be A to the MC. B is going to be equal to dn. X is going to be equal to A to the MD. And Y is going to be equal to NC. And you can see that this works by putting this all back into our original equation, and we get A to the MC to the dn is equal to A to the MD to the Cn. And if you multiply these exponents out, you see that this equation is in fact true. Okay, so for part 3 of this video, we're going to look at some restrictions on the values of capital A, C, and D. So we'll say some restrictions on A, C, and D. So as we noted, C has to be less than D, and C is a natural number, and so we know that D has to be greater than or equal to 2. Okay, but we know that, I'll say also recall, A is equal to capital A to the, or excuse me, X is equal to capital A to the dm, which means that X is greater than or equal to A squared. And then because x is required to be less than or equal to 100, we know that a has to be less than or equal to 10. That is, we're just taking the square root of both sides here. Okay, so perhaps looking at this the other way, again, we have a to the dm has to be less than or equal to 100. But we know that lowercase a, let's see, a is greater than or equal to 2. And capital end is some power of capital A. Therefore, capital A is also greater than or equal to 2. If it were equal to 1, obviously 1 raised to any power is just 1 itself. And so that's not a possible value. Okay, but if we have 2 to the dm less than or equal to 100, we'll conclude that d has to be less than or equal to 6. That is, even if m is equal to 1, you'll note that 2 to the 6th is equal to 64, but 2 to the 7th is equal to 128, and so we know that d has to be less than or equal to 6. And then we can actually write out for different values of d what the possible values of a are. So let's say note, if d is equal to 2, a can be 2, 3, 5, 6, 7, or 10. So we've shown that capital A has to be on the range from 2 to 10, and it can't be a power, and so it can't be 4, 8, or 9 in particular. Now suppose d is equal to 3 or 4. We'll note that a has to be equal to 2 or a has to be equal to 3. So you'll note that if a were equal to 5, 5 cubed is 125, and so that does not work. However, 3 cubed is 27, and 3 to the 4th is 81, both less than 100, so a equal to 3 works just fine. And then we'll note that if d is equal to 5 or 6, then capital A has to be equal to 2. So you'll notice that 3 to the 5th is 243, and so that's obviously greater than 100. But 2 to the 6th, again, is 64, and so that's just fine. Okay, part 4. So now we're going to take a look at some restrictions on the value of b. And so we'll note again that b is equal to dn, so b must be a multiple of d. But we know that d can only be 2, 3, 4, 5, or 6, and so in particular, we'll just say key result, b must be divisible by 2, 3, or 5. Those are the only primes dividing those values of d, and so b must be divisible by 2, 3, or 5. Now this has important implications because let's suppose that we could show, that a squared, a cubed, and a to the fifth all have duplicate representations. That would mean that all values divisible by 2, 3, or 5 less than or equal to 100 would have duplicate representations. Again, this is going back to very early in our analysis when we were showing that we could just take the nth power of both sides. And so let's suppose that we actually were able to show that. How would we go about counting the number of values of that form? So we'll say how many values of b less than or equal to 100 are divisible by 2, 3, or 5. And so first let's look at values divisible by 2. And that's going to be very easy. You just take 100, divide by 2, and you get 50. There are 50 even integers less than 100. Okay, so now we'll look at values divisible by 2, but not 3. Excuse me, the other way around. Values divisible by 3, but not 2. That is, we've already accounted for values divisible by 2, and so now we only want to add the values which are divisible by 3, but not 2. And the way that we'll do that is 100 over 3 minus 100 over 6. And we'll note that this is with integer division. That is, this is 100 over 3 is not 33.3 repeating. This is rounded down to the integer 33. And what we're doing with this expression is, again, we're looking at the values which are divisible by 3, and then we're excluding those which are also divisible by 2. That is, that they're divisible by 6. And so we'll just note that this is going to give us 33 minus 16, which is equal to 17. Okay, so now we're going to look at values divisible by 5, but neither 2 nor 3. Just clean this up real quick. Okay, so in this case, it's actually easier for us to just list out these values. There aren't that many of them. And so this is just going to be the size of the set, which includes 5, 25, 35, 55, 65, 85, and 95. And so that's just going to be 7 values there. So I got these just by looking at the integers from 1 to 20, which are not divisible by 2 or 3, and multiplying them by 5. Okay, so from this, we have number of natural numbers divisible by 2, 3, or 5 less than or equal to 100 is going to be equal to 50 plus 17 plus 7. And so that's going to be equal to 74. Now, unfortunately, when we actually get into looking at the specific cases of our solution, none of them will exactly match this situation. But this, I think, is a good exercise to look at how to count our duplicates in the simplest case. And then for our actual solution, we'll look at the individual cases as we get to them. Okay, part 5, the solution. Okay, and so this is going to have 5 cases. And so basically this is going to correspond to A being equal to different powers of capital A. Alrighty. So as we looked at in the previous section, the simplest situation is when we can show that lowercase a squared, cubed, and raised to the 5th all have duplicate representations. And in that case, we also calculated how many duplicates we would have. Unfortunately, it's not quite as simple as that. But fortunately, this first case comes pretty close. Okay, so the first thing that we'll notice is suppose we have a to the first squared. That's just going to be equal to a squared to the first. Now you might notice that that this 1 here is not actually allowed. That is, our value of y has to be at least 2. However, if we multiply this by, or that is, raise both sides to some power, then we're going to get valid duplicates. But we do have to note that we'll just say over here, note a squared itself is not a duplicate. Okay, going on to lowercase a cubed. So it's going to be a to the first cubed. And similarly, that's going to be equal to a cubed to the first. And we'll say, note, a cubed itself is not a duplicate. And then to wrap up this section, or excuse me, this case, we'll have a to the first to the 5th is going to be a to the 5th to the first. And again, we have a to the 5th itself is not a duplicate. Okay, so now we're ready to determine the number of duplicates for case number 1. So first we want to recall that when the exponent on a is 2, we have 6 different possible values for capital A, and so that's just going to be equal to 6 times 50 minus 1. You'll recall that we, in the previous section, well, let's write it out. We'll say, 100 over 2 minus 1. The minus 1 is because a squared itself is not a duplicate. Now, when d is equal to 3, you'll recall that we have two possible values of capital A that is either 2 or 3. And so we'll say 2 times, and we'd previously calculated that 17 was the number of duplicates. And so then, again, we'll want to subtract 1 because a cubed itself is not a duplicate. Okay, and then we'll add the values of divisible by 5, but not 2 or 3. And again, there are 7 of those, and again, one of those will be excluded because a to the 5th itself is not a duplicate. And so that's going to be 294 plus 32 plus 6 is 332. So from case 1, we have 332 duplicates. Okay, so for case number 2, we're going to set it up in a similar way where we're going to look at a squared squared, a squared cubed, and a squared to the 5th. And we're going to see which of these are duplicates. So for this first case, the only possibility is a to the 4th to the 1st. And as before, we'll note that a squared itself is not a duplicate. And that's again because we have this exponent of 1 over here. Okay, a squared cubed we can write as a cubed squared. And this is the first example where we don't have to exclude the base case. Every multiple of this expression is going to be, or rather every power of this expression is going to be or correspond to an actual duplicate. Okay, and then similarly we can say a to the 5th square, or a squared to the 5th is equal to a to the 5th squared. Okay. All right, so you may recall that okay, so you may recall that looking at our possible values of capital A, once we're looking at powers of capital A greater than 2, most of the candidates are excluded. And so in this case, we're looking at a to the 4th. And so that's going to mean that capital A can only be 2 or 3. And so we're only going to have 2 possible values for that first case. And as usual, this is just going to be 100 divided by 2 minus 1 because we have to exclude that first case. Now the second case, or the second set of values here works for both a equals 2 and a equals 3. And we don't have to exclude the first case. And so this is just going to be 2 times 17. And the third expression here is going to work only for a equals 2, and so that's just going to be plus 7. And that's going to give us 98 plus 34 plus 7, which is equal to 139. All right, on to case number 3. As with the previous two cases, we're going to be looking at a cubed squared, a cubed cubed, and a cubed to the 5th. Okay, now this first case can only be represented as a to the 6th to the 1st. And so obviously that's only going to work when capital A is equal to 2. And so we'll just make a note about that. Okay. Now this case actually can't be represented as a duplicate at all. And you can see that's because the product of 3 and 3 is 9. And so the only other way we could factor that would be as a to the 9th to the 1st. But even for a equal to 2, that exponent is too large. And so we're not going to have values that are divisible by 3. Okay, and then this one can be written as a to the 5th cubed. And again, that's going to be only for a equals 2. And it may seem like that's all the duplicates for lowercase a equals capital A cubed, but we've actually overlooked one of the possibilities, and that's because the lowercase a squared case only works with capital A equals 2, but if we have values that are divisible by 4, if we can find a case where a to the 4th is a duplicate, that might work for for a equals 3. And in fact, that is the case. If we look at a cubed to the 4th, that's going to be equal to a to the 4th cubed. And that's going to work in all cases. Okay, so all right. So in the for the first case, we only have a equals 2. In fact, all of these only one value applies. So even though this second expression here works for a equals 2, we've already covered the even integers with this expression here. And so each of these is just going to be handled separately. Okay, so we'll have 100 over 2 minus 1 plus 100 over 4 plus 7. Oh, actually, we're not using the usual expression in this case because we don't have duplicates divisible by 3. And so we actually have to handle this case a little bit specially. And so that's going to be the number of values divisible by 5, which is just 100 over 5. And then we want to exclude the values which are divisible by both 2 and 5. So that's going to be 100 over 10. Okay, and that's going to be equal to 49 plus 25 plus 10. I believe that's 84. Okay, almost there. Just 2 more cases. Okay, so as usual, we'll look at a to the 4th squared, a to the 4th cubed, a to the 4th to the 5th. Okay, so this first line here actually isn't a duplicate. You'll notice that the only other way of factoring 16 such that one of the divisors is greater than 4, or one of the factors is greater than 4, would either be as 8 times 2 or 16 times 1. And both of those are greater than 6, which is the largest exponent of 2, or the largest power of 2, which is less than 100. And so this is not a duplicate. Okay. Looking at this case, we have the product of the exponents is 12, and so we can write this as a to the 6th squared. And we'll note that this only works for a equals 2. And in fact, because lowercase a in this case is equal to capital A to the 4th, we know that x has to be at least capital A to the 5th, which only works for capital A equals 2. And so all of the duplicates in this case are going to apply only to capital A equals 2. Okay, and then the other case we have here is a to the 5th to the 4th. And again, this is only for capital A equals 2. Okay, so first let's look at values which are divisible by 3. So that's going to be 100 divided by 3. And then we want values of 5 which are not, or values divisible by 5 which are not also divisible by 3. And so that's going to be 100 over 5 minus 100 over 15. So that's going to give us 33 plus, let's see, that's 20 minus 6, so I believe that's 14. Yes, that, I believe that's correct, 47. Okay, and one final case, and this one is actually the easiest of them all because we have C is equal to 5, we know that D has to be equal to 6, and so that just gives us A to the 5th, or excuse me, yes, A to the 5th to the 6th is equal to A to the 6th to the 5th. And that's just going to be 100 divided by 6 is equal to 16. And so our total here is going to be 332 plus 139 plus 84 plus 47 plus 16. Okay, so 99 squared minus 332 minus 139 minus 84 minus 47 minus 16 is 9,183. And if we go back to the archive here, we can check and see that that is in fact our answer. So I know that was a bit of a lengthy video. I appreciate you sticking with me. In the next video, we'll move on to tackling problem number 30.